Okay, good morning again. It's 10 a.m., April 7th, 2020. You can see my screen. The main topics we're going to cover today is conditional branching, delay loops, subroutines. I'm not sure if we're going to reach the lookup tables or not today, or it's going to be next time. We'll do our best. Last time, we started with a project to do delay loops. So I'm going to open that project. I think we called it blink LEDs because we wanted, we did the visualization first, we draw the flow chart, and we wanted to turn on the LEDs connected to port B, delay 500 milliseconds, half a second, then turn off the LEDs on port B, then delay for 500 milliseconds, and keep doing that forever. This is what we started last time. We put a placeholder here for the delay, but we did not write the delay. And this is exactly what we're going to do today. Okay, so let's do some planning before we start writing code. Delays are based, well, we can do interrupt-based delays, and this is going to be in the next chapter, okay? The kind of delays we're going to do here is just wasting the time of the CPU of doing nothing. And we saw there was an instruction called NOP, nope, or no operation, okay? No operation. And this consumes one instruction cycle of the CPU. And Chahad, after we left and stopped recording, asked about, okay, she's confused a little, and I showed something after many of you left, but we did track a code that we already wrote, and simulation single stepping, and we saw that any instruction with one instruction cycle like bit set F or bit clear F took one instruction time period, while the go to took 2 time periods, double, because it had to flush, okay? And this is related to pipelining, as pipelining will save one instruction cycle, okay? So 4 clock cycles from the oscillator is one instruction cycle. If an instruction takes 2 instruction cycles because it has to flush, then it takes 8 clock oscillator clocks, okay? Anyways, to write some code to do a delay of 500 milliseconds, assuming that, actually we're not assuming, the actual oscillator I have on my board here that we're gonna run the code on, the frequency is 8 megahertz, okay? This is the one, the oscillator I have. So we know that the time for an instruction cycle is 4 times the time, which is 1 over the frequency of the oscillator, right? In this case, it's 8 megahertz. And this is equal to 0.5 microseconds. Okay, this is the time for one instruction cycle. So if I want to do 500 millisecond delay, what can we do? So this no operation, nope, will take 0.5 microseconds from the CPU, right? So we need to repeat this one. We need to repeat the 0.5 microseconds a number of times. If we have, let's say, if we have no operation, no operation, no operation, let's say because it's 0.5 to make it just a number with no fractions. Let's say if we want to make it 10 microseconds, then we repeat it 20 times. Okay. 20 times, 20 instruction cycles will take 20 times 0.5 microsecond to execute, right? 1 is 0.5, 20 will take 20. And this equals to 10 microseconds, right? So these 20 instructions will take 10 microseconds to execute. Okay, if we want to do 500 milliseconds, this means we need to repeat this how many times? So if we do the math, 500 milliseconds is 500,000 microseconds, right? Divided by 10, we need to repeat this 50,000 times. 50,000 times to get the 500 milliseconds, right? Well, we can do a loop with 50,000 times, but a loop needs a counter. We know that a counter at the end of the day is, and when you used to write C, you used to say integer counter, right? And then you say counter equals 50,000, right? And every time you start a loop, and every time you say inside the loop counter minus minus, right? This is in C. Well, when you did this, the counter where you assign the 5,000 value into it is a memory location, okay? This is a memory location. An integer in our microcontroller is equivalent to 16 bits, okay? 16 bits, which means 2 to the 16 is 64K, which is 65,536 or something like this. Okay, so it can hold a number up to 65,000. So the 50,000 is okay. But if you say a character or unsigned character counter, and then you say counter equals 50,000, this is not going to work because an unsigned character is only 8-bit. Okay, 8-bit memory location, 8-bit memory location in data memory. Okay, 8-bit memory location can hold up to 2 to the 8. Okay, which is 256 numbers, which is the numbers from 0 to 255, right? So the maximum value you can put in this counter is 255. You cannot put 50,000. Going back to our microcontroller, we know that the data memory, the RAM, we have in the 16F84A or 877A microcontroller is, right, is, well, it's 2 banks, right? Bank 0 and bank 1. Each of these locations is 8-bit, right? So if you go to address 0x0d in memory location and you decide this is your counter, okay, the maximum number, the largest number you can put here is 255 or 0xFF in hex. So I cannot do a counter for 50,000 times easily right now, okay? So we need to break the loop, the 50,000, into several loops. You can do this, for example, 255 times. Then the same thing, we call it inside an outer loop for a certain number of times. And that's what we want to do, okay? And we do the math. So assume we have 20 no operations. This is 10 microseconds. We need to repeat this, the maximum loop time. So let me go down. So if we have no operation, 20 times, no operation. This is 10 microsecond, right? Then we do the first loop. Let's say we'll go to the details of the loop. Loop 1, which is this one, 255 times. This is the maximum, right? Then this loop, if we repeat these 10 microseconds 255 times, then we can get a delay of 255 times 10 microseconds, right? Which is 2.55 milliseconds, right? Now we can say, okay, if we do an outer loop, loop 1, if we do loop 2, that will repeat loop 1, okay, for a certain amount of time. How many times do we need to repeat loop 1? Well, we need 500 milliseconds, and loop 1 takes 2.55 milliseconds. Then the number will be 500 divided by 2.55 will be 196.078. So let's ignore the 0.07 milliseconds. So it's 196 times. So if we execute a loop that calls loop 1 196 times, we get to the almost 500 milliseconds. Okay, well, there is some drift, the 0.07, and the time to execute this instruction itself and this instruction itself, you can add them, take them into account. You'll have a few microseconds drift. And this is the reason why they say, okay, there's a world clock that drifts, I don't know, 1 millisecond every 1,000, this atomic clock every 1,000 years or whatever, because of these drifts or these small differences in such loops or interrupts. Okay, so this is what we're going to do. We're going to write 20 no operations, repeat them 255 times. Then this loop, we repeat it 196 times. Okay, we go back to our code and do this. So the delay here is, first, I'm going to write it as just normal code. Okay, then we'll try to do something more meaningful. So no operation. This will take 0.5 microseconds. Use micro, okay, microseconds at oscillator frequency of 8 megahertz. Okay, so if we repeat this no operation, okay, 20 times, well, you can do it 10 times and you have 3 loops instead of, right? No operation for, I'm not gonna write it 20 times, don't worry. 5, I'm gonna copy and paste, no operation. So operation, so this is starting from here, 1, 2, 3, 4, 5, copy, paste. This is 11, 10 plus 1, 11, right? And I copy this again. Let me copy 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and 11 is 20. Right? Now we have 20 no operations. 20 no operation instructions will take 20 times 0.5 microseconds, and this is equal to 10 microseconds. Now, if we do a loop now we want to do a loop or repeat 255 times. Then we want to repeat the inner loop 196 times. Okay, how do we do that? We need to do a counter where we place 255 in it, and every time this is executed, we decrement the counter by 1, and if it's not 0, we do it again, right? So to do that, we need to put the 255 in one memory location. Please feel free to stop me anytime if you have any question, if there is anything not clear, okay? So we're gonna reserve a memory location. So before starting this, maybe at the initialization here, before the infinite loop here, we can say something. Where do we want to put our counter? We need to put it in a general purpose memory location, a general purpose memory location. Okay. I'm going to open the data sheet. For the, do you want to start looking at the 778 controller? Let's start doing that. Doesn't hurt. Okay, so the memory here, we want to look at the data memory. Now here we have 4 memory banks. We're going to come to the details of this later, but now, assume we still have the 2 banks. Okay, so at 20 hex in bank 0, we have 96 bytes or memory locations free that we can use. Okay, so any address at 20 or beyond up to 7F hex, we can just reserve a location and put any value in it. Okay, so let's start. Let's make a counter at memory location 20 hex. We can do it this way simply. Move lateral to W 0x20. Well, how many times? 255, right? Decimal 255, the first counter. The value is 255 decimal, right? Then we put it in at location, move W to memory, memory address 20 hex. Now address 20 hex is our counter, okay? If you want to make it look fancier, you can say, okay, I want to do this counter, just like what you do in C, and say, okay, wherever I use the word counter, this equates 0x20, and the counter, well, let's say we're going to use another counter, so let's call it counter 1. Okay, counter 1. And when we do counter 2, we do it, okay, at location, for example, 21 hex, right after it. Doesn't hurt. And we want to put the value we want to put in counter 1 is, let's call it counter 1 underscore value is going to be 255 decimal. Right? Or 0xFF if you want. And the counter 2 value that we want to put it in counter 2 is gonna be 196, right? Where did this come from? From our calculations, right? From 196. Then it would be easier here to say move lateral to W counter one value and move it, put it in counter one, right? هيك أسهل. Okay. So counter one will count, well, counter one for loop one at address 0x20 hex in the RAM data memory will count 255 times. Okay. Then we say here decrement F, right? We want to decrement the counter. So imagine you are the program, you are the program counter. You came here, you started this no operation, 0.5 microsecond, this operation 20 times. You did this 10 microseconds. This is the first time. Then you want to decrement the counter, which is the 255, right? So you decrement it, and if it's not zero, you still need to repeat those 20 operations again. So we decrement F and skip if zero, if not zero, we want to skip the following, decrement F and skip, decrement F and skip, if not zero. Why is the color not changing? Let me check the instruction, how it's written. Again, instruction set. Decrement F, where is decrement? Decrement F and skip if zero. Oh, is the, where is the not zero? There is no not zero. I thought there is a not zero, right?
دكتور اللي اخذناهم هم بس انه سكيب اف زيرو للانكريمنت والديكريمنت.
Yeah, man. Are you sure? Let me check the other controller. Is it possible? Let me check. Instruction set here.
دكتور المفروض في skip if هون.
Decrement F and skip if zero. ما فيها؟
دكتور اصلا اللي بدنا اياها سكيب اف زيرو صح؟ لانه احنا رح نعمل سكيب على الجو تو اذا كانت زيرو.
Yeah, you're right. صح. Yes. بس أنا منين إجتني هاي not zero? Maybe from a different controller. Okay. Decrement F and skip if zero. What do we want to decrement? The counter, right? Counter 1, which is the memory location 20 hex, right? Then, if 0, we want to skip the following instruction. If not 0, we want to repeat, right? Go to loop 1, right? And loop 1 will be where it will be at here, at the first no operation, right? This is what we want to repeat. Loop 1. And we initialize the counter. What is this? Turn on the LEDs. Well, I think we can. I think we should do this initialization of the counter, not here. We do it after we turn, because the counter needs to be initialized every time we want to repeat it in lab 2, in loop 2. So we do it here. Okay, so the delay starts here, right? We start, just giving me more space. So this is the initialization of loop 1. Then we repeat. So decrement F it's going to repeat 255 times, right? It's going to go to loop 1 255 times, and this will allow delay of loop 1 to cause a delay of 255 times 10 microseconds, right? Which is equal to 2.55 milliseconds. Okay, this is not enough. We need to repeat this whole loop 196 times. So we need another counter, which we initialized. We initialized it before the first counter. So we do again, move lateral to W, counter to value in this case, which is the 196 we didn't equate up there. And we put it in the memory location counter 2, which is the address 21 hex. Move W to F, counter 2, okay? Counter 2 for loop 2 at address 0x21 hex to count 196 times.
دكتور بس ممكن سؤال؟
اتفضل قيس.
مش لازم يكون انه اوبريشنز اقل عشان احنا ما اخذناش انه الديكريمنت والجو تو انه بالكونسيدريشن تبعنا.
You can consider that. Let me do this. We can delete. Yes, يعني you are right. يعني you want to be more precise, we can do that. If you want to be more precise, this delay, this go to will take two instructions, right? 2 instruction cycles every time.
Yes.
This one, the skip F0, the condition is not going to be true every time, right?
واحد وإذا عملت فلاش بتكون 2.
يعني for 255 times it's going to be 1 صح؟
مظبوط.
So هون عندي 255 instructions will go to is going to be 2 times صح؟
صح.
Except for the last one.
Yes.
It's not going to take صح؟ فصار عندي 3 instruction cycles بدهم يتكرروا 255 times, right? Right? 255 times راح ياخذوا 3 instructions, 765. The instruction is 0.5 microsecond, right? 0.5 microsecond. So these are going to cause 382 microseconds. صح؟ يعني 0.3 أو 0.4 let's say millisecond, صح؟ 0.4 millisecond error. Well, we can fix it by at the end. Let's do it at the end. Maybe ممكن لو نشيلنا no operation واحدة أو نقلل الكاونتر هذا بدل 196 يصير 195. We'll do the math, okay? بس yes, you're right. هذول راح ياخذوا time. بس it's يعني you can neglect it if depending on your application. So
yes,
we'll get back to it. Okay.
Thank you.
So the first loop is actually okay. You know what is 255 2.55 milliseconds. هلا جانا كمان 0.30 قديش كانت؟ I forgot. So 3 times 255 times, right? 3 instructions, and this is times 0.5 microsecond, right? تقسيم 1000 عشان يصيروا millisecond, so 0.38 تمام 0.38 milliseconds. We can add them to the 2.55 milliseconds. يلا let's add them. I'm going to do it right. ماشي 2.55 plus 0.38, and this is 0.93. خلاص 0.93 2.93 huh? If we count the counter and loop instructions, it will be 2.93 milliseconds. And in this case, the outer loop, instead of being 196, so instead of being 500 milliseconds, we'll divide by 2.93. So the counter تاعنا الخارجي will be instead 196, 170. Well, and this 0.6 is not possible. 170 times, okay? ولسه في عندي كمان اللوب الثانية. We'll come to it. Okay, طيب. So this loop, the other loop, will be 170 times if we count the if based on the 2.93 millisecond loop one time. Okay, now we do the outer loop. The outer loop, okay, we initialize the counter. We put 196. نقدر نغيرها. شوف how easy it will be لأنه we did it this way. بتقدر تعملها 171 وخلص. خليها 196 for now. Okay, then once this counter reaches 0, it's gonna skip the go-to and come here, and we want to do the loop 2, right? So we decrement f and skip f0 for loop 2. And if it's not 0, it's gonna execute this go-to. The go-to is gonna go to loop 2, and loop 2 should reinitialize the loop 1 counter, right? Because صار صفر. So loop 2 will be here.
دكتور تحت was decrement of skip of 0 ل counter 2 مش loop 2 صح؟
Decrement f and skip of 0 ل counter 2. Yes, you are right. Thank you. Yes. Now this is also gonna execute هذولا راح ياخذوا كمان 3 instruction cycles for this much of time. So that's how we can do the math really precise. طيب. خلاص, I think we did it. We did it. Then you turn off the delay and you repeat this again. Just copy this again. من هون. Right? And do it here. Do it again. Okay, now loop 1. Okay, صار في عندي loop 1 هون ولوب 2 هون ولوب 1 ولوب 2 تحت صح؟ So you can say okay, counter 1. I'm going to do something easier later, okay? بس هذه counter 1 loop 2 وهذه counter 1. Well, you know what, not counter, what's a proper delay 1? خلاص D1 loop 2, D2 loop 1. Okay, but we need to fix it down there. هون تصير هذه D1 هذه D1. I'm not gonna keep it like that, okay? بس يعني احنا we're building things step by step. وهذه خلاص ما في مشكلة تظل loop 1 loop 2, okay? So look at what's gonna happen. The program counter is gonna start from here, go to main, start here, do the direction of port B, output, then turn on port B, then delay for 500 milliseconds by just wasting time in doing no operation for 255, then repeating this again for 196 times, right? Then turn off the LEDs on port B by clearing it, then doing the loop again of the delay, right? Then you go to forever, you keep doing this blinking on, delay, off, delay, right? Forever, and the forever is here, right? So this is gonna work. If we want to be more precise in the math, we can do that. Let's do it. Let's do it. ماشي. So the first inner loop is going to cost us 2.93 milliseconds. Based on this, the outer loop would need to repeat 170 times instead of 196, right? 170 times instead of 196. So we can just do this 170. Okay, 170 times. 170 times is gonna give us let's do the 170 times 2.93 is gonna take 498.1 milliseconds, right? Now we have these the counter of loop 2. We did not count them. These are 170 times 3, right? 170 times 3. So I'm going to do it on my calculator here عشان أنا أخليها فيك. So 170 times 3 instructions, it's going to be 510 instruction cycles times 0.5 microsecond. Well, that will be 2.255 microseconds, right? Divided by 1000, and that is 0.255 milliseconds. Added to the 498.1, this will cost us 3 يعني هي زائد 0.255. This is the number 498.355 355 milliseconds. And we want 500 milliseconds. How many instructions will we need more? Knowing that instruction cost us, so let me write this down here, 498.355. قيس بتغلب 498.355. Okay. How many instructions are we left with? If we say قديش بدنا minus 500 milliseconds, so we're left with 1.645 milliseconds. We're missing 1.645 milliseconds, right? So let me do this. 1.645 milliseconds, okay, times 1000, this is microseconds, time divided by 0.5, so microsecond. So we need 3,219 no operations more to get the exact 500 milliseconds. Well, we can do this in the outer loop 3,000 or in the inner loop. طيب لو if we ضفنا no operation in the inner loop and divide by 255, okay, then we need to add 12 to the outer loop, right? If we add a no operation here, so we added 255 instruction cycles, صاروا 11, okay, then we need, this needs to be repeated 12 times, so we add 12.9 يعني 13, let's say 13 to the outer loop, well كمان that yeah, 13 to the outer loop, but هذول كمان راح يزيدوا 13, okay, so شوي with a fine tuning 13, so هاي instead of 170 وتصير 183, so we can do this, okay, and my comments are not valid anymore, let's say 183, so هلا كيف صار عندنا الحساب? Let's do it. let's see how much exactly our loop will take. Let's start over. Okay, we have 11 instructions, no operation, repeated. Well, you know 11 زائد 3 بتاعت الانر loop صح؟ 255 زائد 3, this is 14 times 255, okay, times 255, this is 3,570 microseconds. Instructions, sorry, times 0.5 microseconds. This is 1,785 microseconds, repeated how many times? 183, we said, times 183. What happened? It's not 11, it's 21, sorry, again. ما حد منكم يحكي. 21, right? 21 plus 3 is 24, repeated 255 times. Each one costs 0.5 microseconds. This is 3,060 microseconds, repeated 183 times. This is 550. Okay, we execute. we exceeded the let's say 3060 times 180. 3060. You know what? Let me do it this way. 3060 times, instead of 183, 180. No less. 3060 times, this is in microseconds, right? Times 70, 520 نقصوا. طيب 3060 times 165. Okay, رجعنا نقصنا. Maybe 3060 times 166. Okay, 07. شايف يعني 160 at 165 في زيادة, and this is how much? 7 milliseconds drift. So you need to do the math better than this. Yani we don't have the luxury of time. We have a drift of few milliseconds. So we'll stick to this, okay? Instead of, so 183, I'm going to go back to 170. It's almost half a second. It's almost half a second.
دكتور
Yes, تفضل.
بزبط بس لو سمحت هيك ترجع تعيد الفلو بسرعة لأنه شوي صغير هيك يعني.
Okay, I am going to do that. I am going to do that. The flow is, first, you go to, when you start your controller, your program counter is going to go to my main here. Select bank 1. Set TRISB to be output. يعني port B is output. بعدين اكتب go back to bank 0 واكتب في port B FF يعني ones. يعني turn on all the LEDs on port B. بعدين we go to the delay. The delay is عبارة عن two loops, outer loop و inner loop. We call them loop 2, loop 1. Okay, loop 1 has 20 no operations. Okay, so you're gonna come here. في counter 2 اللي هي address 21 hex في الميموري راح يحط فيها value اللي هي 1 قديش كتبناها فوق 196 or 170 قديش كانت 170. Okay, 170. بعدين الانر لوب counter 1 اللي هو at 20 hex راح يكتب فيها 255. بعدين no operation 20 times. بعدين ينقص 255 إذا ما صارت zero go back to no operation 20 times بس يخلصوا ل 20 times هاي 20 مرة بروح على counter 2 بيعملوا decrement هاي ال 170 بتصير 169 بعيدها 170 مرة وكل مرة بعيدها برجع سات شوف الاوتر لوب تيجي هون برجع يعمل الانر لوب 255 سو 170 مره بتتكرر ال 255 مره بتكرروا 170 صح في 255 بعدين you go to port B يعني you clear port B يعني طفيت ال LEDs وبعدين you repeat الديلي كمان مره اوكي خلصنا so this is gonna work we don't have a lot of time to make it work now بدي اعمل شغله يعني عشان do two in one okay يعني for what we did here we're wasting some resource and we know that embedded systems are resource constrained systems right we are limited with memory one of the main things data memory and program memory what is the big bad thing we did here see this delay how many memory locations did it consume in the program memory and when this is converted when we convert this to machine code how many instructions do we have 1 2 and then here 20 right 22 23 24 25 26 memory locations and then again in the second time we do it we have command 26 memory locations these are program memory very this expensive resources you cannot afford doing that every time you want to do a delay so it is better to put it in something we call a subroutine and we just call the subroutine and that way you can call it as much times as you want yet consuming program memory space only once right so this is what I'm gonna do I'm gonna cut this okay I'm gonna delete this and say instead of where was the okay see okay I'm gonna do this delay I'm gonna instead of saying I'm gonna write a subroutine called call there is an instruction called call okay my delay I'm gonna write a subroutine called my delay okay my 500 millisecond delay let's call it call my 500 millisecond delay and this is a subroutine I want to write ماشي I want to write it here I copy I want to go write it here in the bottom after everything after the go forever here I'm gonna write a delay for 500 millisecond here and if this is gonna be actually what we did here right I'm gonna cut this and put it here loop 2 loop 1 everything perfect and بس آخر شيء لأنه هذا call so أنا what did I do value counter 1 counter 2 I did not take the counter 2 صح I take هذا كمان معه I put it here قبل loop 2 we initialize it we initialize the counter before we start the loop but it should be in the subroutine and I mentioned what is a subroutine I'm going to go over it again right now okay so all what we need to do right now هذا we can delete it we can delete all of this we say call my 500 millisecond delay here then we turn off the LEDs then we do we call my 100 milliseconds delay again right? Then we go to forever. So look at our main loop. This is our main loop. Yeah. See, this is our main loop. This is the main, our core business here. We turn on port B, we delay 500 milliseconds. We turn off port B, we delay 500 milliseconds, doing this forever. Now, what does this call do? I explained it when we were studying the instruction set. Call means push the program counter, the current program counter, to the stack. When you are executing the call instruction, the program counter is pointing to the next instruction, to the clear. Okay, push it to the stack to use it later, and make the program counter point to this location I described here. Okay, so the program counter will go here, start executing this code until the end. Then I write at the end of the subroutine, return. The turn will go and pop the top of the stack and give it to program counter. After executing the return, the program counter value will go back and point here to the clear F where it was before the call, when we did the call. بعدين بعمل clear F, turns off the LEDs, then call again. So when you do the other call, the program counter is pointing at the go-to. This will be pushed to the stack, and the program counter value will go again here and initialize the counters and do these loops for 500 milliseconds, then return. You go back to where you were before the call at the go-to, and you keep doing this forever. See the advantage here. We saved, this occupied only, how much was it? 26 memory locations? Only once. But we can call it as many times as we want. This is what we call a subroutine. In high-level languages, in C, you used to call it a function, right? Okay, so let me build this program and program it real quick before you leave, show it, see if it works or not. Project, build all. Hope we didn't forget anything. Failed, fee problem here. What is the problem? Debugging, processor symbol. There's a problem. Clean, execute. Halting build on failure request, last demo blink, LED. What is the problem we did here? Okay. Origin 0, program origin 20. Quait.
دكتور بالكول الثانية نسينا نحط اسم ايش بدك تعمل هاي.
هاي.
الكول الثانية لازم ما يفوت.
هاي ثاني صح؟ هاي منين جبتها أنا؟ يس. clear up port B. الكول الثانية هون. شكرا يا قيس، والله أنت you're helpful. يعني كان ضيعنا هسه نص ساعة. Trying to figure it out. Successful, see, small problem. Okay, built. I'm going to program it now. I'm going to go to my programmer. I'm going to read, I'm going to load my hex file from the memory location we saved it at, which is demo blink LED here. Open it. Choose our oscillator to be high speed and disable the watch timer. Then we write our program memory. Okay, I'm gonna switch meanwhile to the other camera. I'm gonna stop sharing my screen so you can see the camera. Where's the camera here? To the USB camera, and you see the LEDs blinking, except for that dummy one that didn't work last time. It looks like we have a problem with that LED. But next time we'll use another port. You see it blinking? إذا بتعد معه.
Yes, دكتور.
It's almost half a second صح؟ يعني بين ما يضوي ويضوي مرة ثانية. 1, 2. I think it's precise. To be more precise and accurate, if you want, you can just put an oscilloscope on any port B0 or 1, and you can see how it goes to high and low and see the exact timing. But unfortunately, I don't have an oscilloscope at home. But you can also simulate it in MP Lab. Okay, I hope we got to understand today the conditional branching, the subroutines, and how to do the math to compute delays. Okay. Next time we'll finish the rest of the chapter, lookup tables, and hopefully we start with the micro C and start writing our first C program. Any questions before I stop the recording related to what we discussed today?
دكتور أنا عندي سؤال.
تفضلي سورة. Do you want it to be on the recording or what?
لا عادي.
Okay, تفضلي.
اوكي. ما في طريقة تانية إنه تكون مثلاً ديلي غير هاي الطريقة بالMD Lab أو
في interrupts and it is more accurate. Okay, this is what we're going to cover in chapter 6. Hardware based delays, we call them hardware based delays based on interrupts, exact timing. We're going to do it. Okay, but this is a way to learn how and to recognize the difference between interrupts and execution loops. Okay. Okay, I'm going to stop the recording. Thank you very much. You can stay if you need more questions. Thank you.
دكتور هسه بس للي ما شاف